Welcome to the second lecture on embedded systems course. In this lecture, we shall focus on the architectural design of embedded systems and to identify the hardware and software components in it. These days, when we talk of designing and implementing embedded systems, it is not just a block of code implemented to execute on a processor, but it is rather a more fundamental design question of partitioning the components into hardware and software components to figure out which part of your system is going to be implemented in hardware, which part of the system is going to be implemented in software, and then have a co-design of the hardware and software components. So if we talk of the architecture, basic architecture of an embedded system, it is more of a layered architecture where you have the bare hardware and sitting at the core of the system, and then on the top of it is a layer of operating systems which basically talks to the hardware by providing signals to the hardware, and also has interfaces with which it interacts with the application program, which is more meaningful to the end user. So the real hardware is hidden from the end user by means of this application software and the operating systems. On the other hand, people can safely operate the system by giving some queries to the application software, which basically talks to the operating systems, and then the operating system talks to the hardware. So if we talk about the basic architecture of the embedded hardware, it consists of a processing unit. But then the processing, but as I said that today when we talk of embedded systems, we are not having systems which are implemented only in hardware or only in software, but rather we have something called a hardware software co-design. So we have to figure out the critical parts of the system with respect to the criticality in delays and criticality in processing and so on, which are essentially to be implemented in hardware with using FPGA or ASIC. But on the other hand, the less critical components, which means where you can have some I/O functionalities, where you can have some slower applications which are not so critical, that can be implemented on software, where a block of code may be written to have a sequential fetch, decode, and execution of instructions using the CPU. But then this processor and the FPGA or ASIC constitutes only the processing core of the system. It has to talk to the real world, for which there are AD, analog to digital converters, and digital to analog converters. The analog to digital converters accept inputs from the sensors or transducers and performs a conversion of the analog signal to the digital signal, which the CPU can compute on. The CPU again produces the digital signal, which has to be converted into the analog form before it can be used for actuation purposes, which makes sense to the end user. The software components consist of a plethora of components such as device drivers, then file management systems, then multitasking, multimedia preemptive systems, hard real-time systems, and so on, which are basically used for talking to the hardware as well as talking to the end user. So depending upon the complexity of the systems, either there will be a single layer of software which with well-defined interfaces with which the end users can talk to, or there can be an embedded layer where the operating systems is there, which is much closer to the hardware, and there are also interfaces with which it talks to application programs which the end users are more comfortable with. So it actually depends upon the application complexity whether to have a single layer of software or two layers of operating system and application program, depending upon the particular application for which it is being developed. So the characteristics of an embedded system are marked by the kind of processors we have, the user interfaces, the tools which are used by the embedded systems for debugging purposes, the reliability of the system, So when we develop embedded systems, we should have facilities for easy debugging of the system. We should have a system that runs faithfully over a long period of time. There should be a well-defined user interface. And so coming to the basic architecture of the system, it depends upon the kind of embedded core we are using. Now, if it is a general purpose processor, it is basically based on sequential fetch, decode and execution of instructions. In case of a general purpose processor, the data path is general, but the control unit doesn't store the algorithm is programmed into the memory. So, so depending upon the type of processor, the instructions are fetched sequentially from the memory, and then they enter into the instruction register where they are decoded, and based on the instructions, data is being passed to the data path, and in course they are computed upon with the help of control signals being issued by the control unit, and the computations typically take place in the ALU, and the results are stored back in the registers. The control unit basically issues the control signals to regulate the flow of instructions and ensure the instructions are executed in a timely manner. They perform the controlling of the different operations involved in the execution of instructions, like the fetching of instructions, decoding of instructions, then perform the basic execute operations in the ALU, and then they also fetch operands to compute on and store the results in the back in the memory. So when we talk of choosing the particular embedded core, we have to answer the questions like what is the resolution of computation we need? Should we go for 8-bit, 16-bit or 32-bit processors? And because the larger the bit length we go for, there will be more power dissipation. On the other hand, the accuracy of computation will increase because we have now the resolution of computation is spanned over a larger number of bits, which means the error in computation will be less. One of the important aspects of choosing the processor is the clock frequency. The clock frequency must be sufficiently high to produce the results within a reasonable time frame, and it should be sufficiently low to ensure that not a lot of power is being dissipated. So it is again an optimization problem to solve. What should be the right clock frequency for the particular application being concerned? Typically, we for a certain clock frequency, we keep on increasing the throughput by going for pipelined architectures, where we ideally expect to have one instruction being executed per clock cycle in the steady state. To further boost up the speed of execution of instructions, improved architectures such as Superscalar and VLIW architectures have come, where you have more than one instructions executed per clock cycle. In case of Superscalar processor, you have a set of ALUs to support more than one instructions per clock cycle. In case of Superscalar processors, instructions are fetched in batches and executed as many as possible through parallel data paths. On the other hand, in case of VLIW instructions, each instruction word is basically a compound word with multiple simple instructions within it. They are fetched in one go and decoded and executed parallelly. So these are the two approaches by which we can increase the speed of computation to more than one instructions per clock cycle. So when we actually design and implement an embedded systems, it has to go through the typical way by which a system is being designed and implemented. First, we should have the requirement specification. We should understand the requirements of the system and then prepare an unambiguous specification of it. Then we should do the architectural design and then translate it into the interconnection of components, and finally we shall do the system integration. So there are two approaches of design. One is the top-down approach and the other one is the bottom-up approach. In case of the top-down approach, we start with the most abstract level description and approach towards the most detailed form of description. In case of bottom-up design, we start with from the simple components, implement them, and then integrate the working of the simple components into the working of the whole system. The real practical designs actually make use of both the approaches, which gives us best results. At each level of abstraction, we must analyze the design to determine the characteristics of the current state of the design and refine the design to add details. And when we prepare the requirements, we have to repeatedly interview the customer to understand the requirements of the customer, and then in between our developments we can provide prototypes to the end user for their comments, which can serve as efficient feedback inputs which may be taken for further improvisation in the development. So if we categorize the total set of requirements, we will come across functional as well as non-functional requirements. In case of functional requirements, we are not concerned with the internal structural details of the system, but we basically look into the system as a process taking a certain input and producing a certain output. But that is also not sufficient, because we have to look into other aspects such as time needed to compute the output, size, weight, power consumption, reliability, and so on, which are the non-functional requirements of the system. So in this slide we can see our requirements form, which basically consists of the parameters as mentioned, and based on the requirements we basically prepare a detailed specification which consists of a precise definition of and description of the system. It may not imply a particular architecture, but provides input to the architecture design process. The specification may include functional and non-functional elements. It may be executed or may be available in mathematical forms or proofs. So if you let us consider a type system, which is a global positioning system, to see how it is basically designed at an architectural level. So in the GPS system, the map data is obtained as input through an user interface, and there's an user interface through which the map is being taken, and then operations are required to satisfy the user request, and then there are background operations that are needed to keep the system running, and then it should provide the information to the end user after providing an appropriate level of rendering. So first you have to answer the question that what are the major components that go regarding the specification with respect to the hardware and software. So if you consider the basic block diagram of the system, you can see the basic components like the receiver system, the computing system, the image processing system, the display system, and so on. Now coming to the hardware part, we need a display system to display the final image. Then in order to do the display, we need information from a frame buffer. In order to get the information to compute on, we need a memory to store the information. So there are input and output interfaces to talk to the system, which basically makes up the hardware components of a system. When it comes to the software, there are definite components like the renderer, the image processor, the decision maker, which basically computes on the image data and applies rendering to it, and then produces output after doing appropriate rendering. So while you are implementing the embedded systems, you must spend time in architecting the system appropriately before you start coding. Some components are ready-made, some can be modified from existing designs, others must be designed from scratch. But when you are integrating the system, be sure to keep on checking for the bugs at each and every stage. If a bug is not catched on time, it can create a lot of problems at a later stage of the design process. In fact, catching a glitch in time saves 9. So when it comes to the application of embedded systems, the applications are varied and widespread. It ranges from medical applications to networking to office automation to industrial control to consumer electronics and whatnot. And all these applications have become a part and parcel of our everyday life now. To summarize, we can see embedded computers all around us. Many systems have complex embedded hardware and software. Embedded systems pose many design challenges like design time, deadlines, power dissipation, etc. So we have to adopt appropriate design methodologies to help us manage the design process. So this brings an end to this current lecture. Thank you.